Awesome. Can everyone hear me? Welcome, everyone. Thanks for joining. This will be the AMC 10A Livesolve from this year, from yesterday's test. Hopefully, everyone here has done the AMC 10 or 12 and is excited to work with me through some of these problems. Some reminders before we start. Just be respectful in chat. Try not to give too many spoilers. I probably won't be reading the chat too closely, so you don't have to worry about that too much, but there's a chance that I'll accidentally read something that I shouldn't, so just be mindful of that. Yeah, so then for the AMC Livesolve we'll have right now, we'll do 75 minutes of the actual test. We'll see how I score, and then we can talk about some of the things I was thinking about during the test. All right, nice. Yeah, so you're probably just gonna get started in a couple minutes. Yeah, but there'll be plenty of time for questions later. And as a quick reminder, there is a 7 p.m. slot for the AMC 12A Livesolve. So that'll be also really fun. So make sure to tune into that as well. For those of you who don't know me, I'm Adam. I've worked with AlphaStar for many years now, on and off. And hopefully I'll continue to be of good help. So I think this will be really fun. We'll get started in just a couple, maybe in the next minute or so. All right, so let's start at like 5:07. I'll set a 75-minute timer and then we'll get right started. Yeah, actually I tend to do better on the AMC A's rather than the B's. I feel like they're better. Maybe it's just like happen to be lucky, but I feel like I've always historically done like 6 points better on the A than the B. Maybe it's just an artifact though. I don't know if it's a real effect. We'll see how I do. Hopefully I'm not too washed. All right, 5:07. Let's get started, guys. All right. I'm just gonna take like a minute or so to just read these problems. 8 miles per hour. Right, and then I'll put my work on the left here. Given a 1 hour head start, gives them 8 miles, and then each hour is 4 miles, so 2 hours after 2:30 gives E. I guess I'll have to like keep track of my answers somehow. Yeah, okay. I have trying to figure out how to pan. Okay, pan is right click. Like, let's continue. Box contains 10 pounds of a nut mix that is 50% peanuts, 20% cashews, and 30% almonds. And then 20, 40, and 40. New nut mix. Okay. So 50 and 20 to get 40%, that is 2/3 of the way between 20 and 40. So we must have had 1 part this and 2 parts this. And we know the first one is 10 pounds, so this must be 5 pounds. And so we have now cashews is 2 pounds from here, plus 5 pounds, 40% cashews is another 2 pounds here, for a total of 4 pounds. Number 3, how many isosceles triangles are there with positive area whose side lengths are all positive integers and whose longest side length 2025? Okay. Isosceles, okay. So there are many cases where we have, so this number can be 1013 all the way up to 2025. Furthermore, if the 2025 is here, this number can be as small as 1. and it goes up to 2025. But make sure we're not double counting the equilateral case. So there's 1013 cases here plus 2025 cases here. Total is 2025 plus 1013 minus the one case we're double counting. And the equilateral triangle is isosceles, so we should be counting it. Yeah, so that's 3037. I'm surprised 3038 is not an answer here. Maybe I'm doing something incredibly silly, but I think this is correct. All right. New students going to compete against a team of teachers. Oh, sorry. The total number of students and teachers is 15. Ash wants to join the contest. The average age would increase from 12 to 14. So that's a change of 2. The average will decrease from 55 to 52. Okay, I see. So, so let there be like S students and T teachers. Then if you increase something by from 12 to 14, then however old Ash is plus the total age of the students, which we'll call big S. Guess I should. So, okay. Okay. And then you can also do the same for the teachers. We go from 55 to 52. So the total a plus 55t over t plus 1 is 52. So that gives us a plus 53t equals 52. And then we can cancel out the t and the s here, recalling that, okay, the 2s plus 14, 52. I see, sorry. Keep moving it this way. Okay. I feel like, yeah, and then the total, remember the total is 15, so s plus t is 15. 30 plus 14 plus, this seems wrong. What did I do? Sorry, a plus 3t equals 52. That makes more sense. So this gives us t plus 30 plus 14 equals 52. T is, what is this, 8. S is 7. This gives A is 14 plus 14, 28, or 24. 52 minus 24, which is also 28. Cool. Move on to number 5. One, two, one, two, three, 2, 1, 2, 3, 4, 3, 2, 1, 2, 3, 4, 5, 2, 4, 3, 1. I see. So 1, 2, 1, 2, 3, 2, 1. Okay. So after the nth occurrence of 1, where are we? Well, how many terms have there been? Well, suppose, let's see, we start with 1, then we go to 3, then we add an extra, so we start with 1, then we add another 2, and then we add another 4, and a 6, right? So the nth occurrence of 1 occurs at the 1 plus 2 plus 4 plus 6 and so on term. So what's the closest we can get? 2025th term, it's well known that 2025 is 45 squared. So we can get pretty close by, it's sum of even numbers, which is like pretty close to square numbers. It becomes 44 times 45 is the closest one. So we add up to 88. I think that makes it like 2 times, 44 times 45 over 2. And so that becomes 1981. So that would have been the pyramid that goes from 1 to 44 down to 1. Sorry. I think it's 45 down to 1. So that would have added 88 terms here. Then from 1981, we need to go forward 44 more, so we end up with this, the number 45 here. That would give us E. I feel very unsure about things now. Maybe this is just because I'm no longer like super into math, like haven't been doing math competitions for a while. But hopefully we'll have some time at the end to check our work. Equilateral triangle, each interior angle is trisected. Okay. Something like this. Oh, equilateral. What am I drawing? Okay. And then the intersection of the interiors is the interior of a convex hexagon. Okay. What is the smallest angle of this hexagon, which would be this angle here? 20, 20, this is 120. And so this angle here this is 60. This is 10 degrees. So then in this case, we take this triangle here, which has degrees 10. What did I just draw? Sorry, this should go through here. So 10, 60, and so this angle here is 110. What am I doing exactly? These are 20-degree angles. This is 40 degrees. This becomes 70 degrees. 70, 70, 50, 50. This is 100 degrees. Bit messy. 7. The remainder is 4, so then that gives us instantly that a plus b is 2. And then 8 plus 4 plus 2a plus b is 6. So 2a plus b is negative 6, which makes a negative 8, and b equal to 10. B minus a is 18. At least one of these statements is true. At least 2 of these statements are true. At least 2 of these statements are false. At least 1 of these statements is false. How many? Okay. These things are true or false. Let's say, so greater than 1 equal to 1 true, greater than 1 equal to 1 true, greater than equal to 1 false, greater than equal to 2 false. Let's see. Let's say this is true here. There are at least 2 true statements. Yeah, Yeah, so how many true statements are there? If there's two true statements, then this is true, this is true, this is true, and this is true. Bad. If there is one true statement, then this is true, this is false, and these are both true, which is also bad. If there are three true statements, this is true, and this is true, but this is false. So we have three true statements and one false statement. That makes sense? So we have one false statement for B. Let's not look at number 9. Let's see. So 1 comma 25. Interesting. So what does this graph look like? So it's like 100 times x squared minus 3x plus 2. And that we see when this is equal to 25. So x minus 1, x minus 2 is equal to 1/4. Let's see. Let's just graph this out. So at 0, at 1, and at 2, we have roots. The graph goes up from here and it goes down from here. So this is like x minus 1 all cubed minus x minus 1, right? I can't see any like immediate roots, so we'll just have to wonder if there's some point where this reaches 1/4. Let's see, like for example, if we plug in 1/2, 1/2 times negative 1/2 times negative 3/2 is 3/8, so that doesn't reach. Yeah, where is the local maximum here? Because you can cheat a little by using calculus, but there's probably an easy way to figure out whether this reaches 1/4. Yeah, so we can see that the maximum here is reached by, so it's x cubed minus 3x squared plus 2. This reaches the maximum when x squared minus 6x plus 2 is 0. X is like 3 root 7 over 2. So then, sorry. So that gives us, at 3 minus root 7, we reach our maximum. 3 minus root 7 is like 2.6 something. Okay, I see. Yeah, so probably we don't, it just becomes like, yeah, we can see that this does in fact reach 1/4, for example here. So that means we do reach 1/4. So then there's 3 roots here. And so it's just asking like how many shifts are possible such that that makes that work. In this case, there are 3 instances where this is true. Like we want it to happen here. So 3 different shifts. So really the answer should be D. Number 10. Semicircle here, smaller semicircle. What is the area of the resulting figure? Yeah, so you can actually just center that first of all. And this is 16. So so you have like big R, big small r, and this is 8, right? So then r squared minus small r squared is 64 by the Pythagorean theorem. Oh, but then like the area is just half pi r squared minus r squared. that gives us 32 pi. Nice. Let's go 11. The sequence 1 x, y, z arithmetic, 1 p, q, z. So same starting and ending. And z is as small as possible. Okay, interesting. Yeah, so what does this mean? That means that z is divisible by 3. Or sorry, z is 1 mod 3. So it's a multiple of 3 plus 1. And this is geometric. For a geometric series to start with 1, it has to be some perfect. So z is also a perfect cube. That is 1 mod 3. Clearly, z is not, or we can't just use n as 1, so we have to use n equals 4 as in the next case. So z is 64. So what are the totals? 1, x, y, z, so then that becomes difference of 21. And then 1 for 16, 64. So then that gives us x, y, z, p, q. Add up to, let's see, 43 times 3 is 129 plus 20, 149. Just making sure I don't, there isn't some like weird catch here. I think it should be fine. We'll revisit this question later. 12. 4-digit passcode. Exactly 1 digit is even. 1 possibly different digit is prime, and no digit is 0. So let's do casework. The first case is like what if the digit is 2, then these numbers are exactly 1 digit is prime, so the remaining numbers are not prime and they're not even. So the numbers can be 1 or 9. So that gives us 4 ways to place the 2, and then 2 cubed ways to pick those. It gives us 32. And then if we don't have 2, then we have like 3, 5, 7. Then some number 2, 4, 6, 8. And then numbers that are not 3, 5, 7 or 2, 4, 6, 8. So that would be 1 or 9 again. So then you can see that we end up with this. There are 12 ways to arrange this, and then 3, 4, 2, 2. So that gives us 144 times 4, 576, plus 32, 608. There's so many, seem to be so many E's. I'm a bit worried now from this, but I think we'll be fine. Number 13. Infinitely many squares, same center, and the ratio of the side length is k. Okay, and it turns out that the total area is 64%. So the total area can be represented as, let's say the outer square has side length 1, then we subtract out to k squared, and we add k to the 4, then we subtract k to the 6, and so on. Remembering that the area is the squared version of that. And so that's just 1 over 1 plus k squared. And we want that to be 64 hundredths. Then k squared is 36 over 64. So k is 6/8. Is 3/4. That makes sense, right? 3/4. 9 over 16, 25 over 16, 1 over that, 16 over 25, which is 64. So we get the 14. 6 chairs, 2 students, 2 teachers. What is the probability that the 2 students will sit in 2 adjacent chairs and 2 teachers will sit in 2 adjacent chairs? Let's see. So students and teachers. Let's see, there are 6 ways to seat the students. Then that leaves 4 remaining seats, so 3 different arrangements for the teachers. So that's how many arrangements work. And if we treat students and teachers as indistinguishable, then the total number of ways to arrange the students and teachers is 6 choose 2 times 4 choose 2. Those cancel, and we end up with 3/15, 1/5. Does that make sense? Because, okay, let's fix a student, and then the other student has like a 2/5 chance, and then the probability that the teachers are now adjacent is 1/2. Yeah, so there are 3 cases out of 6. Yeah, so this gives us 1/5. B. Let's look at number 15. ABEF is a rectangle, AD parallel or perpendicular to DE. AF is 7. Oof, okay. AF is 7, AB is 1, and AD is 5. Okay, so this is a 1 by 7. And then this length here is 5. Okay, thick. Hopefully this crude illustration will work. What is the area of triangle ABC? Okay, so we know that we always draw common lines here. So for example, this diagonal here, that would give us that this is a 5√2. So this is in fact a 45, 45, 90 triangle that we've just drawn here. And then that gives us that this whole thing is 5√2. This here it has to be such that this is a 45-degree angle, and then this is like some angle theta. So then let's just say like tangent of theta, because that's easiest to compute. Tangent of theta is the tangent of like the arctan of 7 minus 45 degrees, so arctangent of 1. That just becomes 7 minus 1 over 1 plus 7 times 1 is 6/8, which is 3/4. So in fact, this length is 1, so this length is 3/4, and our area is 3/8. That gives us a... Number 16, there are 3 jars. Each of 3 coins is placed in one of the 3 jars, chosen at random independently of the placements of the other coins. What's the expected number of coins in a jar with the most coins? Okay, so there are 3 separate cases. One of them is like all the coins happen to be in the same jar with probability 1/9. 2 are in one, 1 in the other, and then 0 in the last one. This happens with so how many ways are there to do that? Out of 27 different possible ways to arrange the 3 coins, there are 6 times. There are 6 ways times 2. Sorry, 6. Let's see. Like if we label the coins A, B, and C, then there are 6 ways to pick which one has 2, which one has 1, and which one has 0, and then 3 ways to figure out which one is the solo coin here. So that's 18. So there's a 2/3 chance here, or 6 in 9. And then finally, all of the coins are separate with probability 6/27. So that gives us 2/9. So then the total expectation is in the 3 with probability 1/9, 2 with probability 6/9, and 1 with probability 2/9. That gives us 3 plus 12 plus 2, which is 17. Right. Okay. Yep, 12 plus 5. Makes sense. Okay. Number 17. Let n be the unique positive integer such that dividing the number 2, 7, 3, 4, 3, 6 by n leaves a remainder of 16. And then 2, 7, 2, 7, 6, 0 by n leaves a remainder of 15. Okay, interesting. So n is clearly at least 16. Sorry, greater than 16. And further, we need some, okay. That means for this to be true, then we're looking at 2, 7, 3, 4, 2, 0 and 2, 7, 2, 7, 4, 5. The number must divide both of these, so the number must divide their difference. In this case, that would be 675. Okay, yep, and n is greater. Okay. We also know that it must, yeah, so let's just do the Euclidean algorithm now. 2, 7, 2. Clearly, 2, 7, 2, 7, 4, 5 is divisible by, okay, what's the prime factorization is? 3, it's 3 times 225, and 225 is 3 squared times 5 squared. So it's 3 cubed times 5 squared. Let's divide this by, we can see that this is divisible by 5, but not 25, so we can divide that first. And we can also just divide by 45, because we know this is divisible by 9 as well. Sum of digits is 27. So this gives us, what, 6, 270, 2745, 6, 0, 6, getting confused, 27, 0, then 6, 45, and then 1. So this is not divisible by 3 further, so that gives us 3 squared times 5, or 45. All factors of 45 are less than 15, less or equal to 15, except 45 itself. So in fact, this must be the final answer. Yep. Okay, so the answer is 45. The tens digit is 4. The harmonic mean of the real roots. Okay, this will be fun. The product of k squared minus 4x minus 3. Ugh, okay. Right, so what are the roots of k squared minus 4x minus 3? Each of these polynomials has either no real roots, one real roots, or 2 real roots. So we just see, okay, when for what k does this have real roots? This should always have real roots, right? Because the discriminant here is 16 plus 12k. So then we're happy. So what we really need to find is sort of like, okay, given that since all of these have have only real roots, we can just now say that there's 4050 of these, and we need to find sort of this expression here, right? Which looks, I mean, one thing we can do is just like actually just calculate this. We know that the real roots come in pairs. So for example, like 1 over r1 plus 1 over r2 is equal to the sum r1 plus r2 over r1, r2. And so if we have a polynomial here, the sum of the roots is 4 over k. And the product of the roots here is negative 3 over k. So we just end up with negative 4/3. Regardless of k, So then we just end up with 4,050 times 1 over negative 4/3, and there's 2,025 of those. That becomes 2 times negative 3/4 or negative 3/2. In particular, even if we have sorry, the sum of this is 4 equals 0 is 4. Right, so then we end up with this answer here. And this turns out to be true no matter how, like the 2025 here is irrelevant, which is nice. Happens to work out that the harmonic of each pair is always the same. And it happens to be negative 3/2. 2 over 4 over negative 3, 2 over 30, 3/4, 3/2. Okay, nice. Number 19 here. There's the numbers negative 1, 3, 1, and then we do a Pascal thing here. Okay, nice. If the process continues, one of the rows will sum to this number. Okay. So our question is, first of all, yeah. So like, what is the sum of the things? Well, I claim that it will double every turn because if we have some row of numbers, then each number is represented exactly twice in the resulting thing. And we add those all together and we see a double. So 12,288 is, we start with, so this becomes 4,096, well-known number, 2 to the 12. So we start from the first row that has negative 1, 3, 1. We have to go down 12 rows. So this is like row 1, 2, and we go to row 13 then. The numbers here on the left will be 2, 1, 0. In general, the number there is 4 minus I, so it becomes negative 9. And this becomes 4, 6, 7. In general, the third number from the left will be 1 plus 3 plus 2 plus 1 plus 0 all the way to negative 8. For each row that we're adding, we're adding a new number. In particular, the last one will be negative 8. And so that becomes 1 minus 4, 5, 6, 7, 8. That becomes negative 29. I'm really not a fan of all of these numbers that are so close to the edge here, like A or E. But we're just here to do a first pass through. We'll come back to this. A silo, I just like mark this actually, something I want to check. A silo with diameter 20 meters. I think this is like a 2D problem, low-key. No, actually. So, or like we want two diagrams here probably. So here, diameter 20 meters. 20 meters west, 15 meters south. McDonald. And then McGregor is located 20 east and some amount south. Okay, the line of sign. Okay, I see. So then we also have this. Okay, yep. 20, 15, 20. These are equal. So then this is 25. This is 10. Then this is some angle. And then if we extend this, yeah, so what is like this length L basically? So then we have a height of 10, we have a 25 here and this angle here. So then the total angle here. So then we have another tangent situation. Let's say theta and phi. Tangent of theta is 4/3. Tangent of phi is, or that is a bit annoying. So you can use, so this becomes like this triangle, 2, 5. This becomes root 21. So it becomes 2 over root 21. The tangent of the sum, this is gross, but we'll do it. So the tangent of the sum is 4/3 plus 2 over root 21 over 1 minus the product, 8 over 3 root 21. Let's multiply 3 by 3 root 21, 4 root 21 plus 6 over 3 root 21 minus 8. Oh, that bottom, that is, it's a bit annoying, but we'll keep it in this case here. Tangent here, so then the total L, I guess like this total length we should call L. L over 15 is this number, so then L is 15 times this. And then now that we have L, we can calculate here. This length was 40, so L minus 40 of 15 by similar triangles here. So then that's a pretty sad looking expression. Let's replace this with 1 minus 40 over L. So you just need to figure out what 40 over L is. Whew, okay, let's do it. So 40 over 15 times the reciprocal here, 3 root 21 minus 8, 4 root 21 plus 6. What 40 over L? What is that bottom? That becomes 4, so 4 root 21, 16 times 21 minus 36. Oh, that ends in 0, so that's nice. 320, 336 minus 36, this becomes 300. So this, 3 root 21 minus 8, 4 root 21 minus 6 over 300. What does that top become? Let's see, 40 over 15 times 3 and 4 times 21. 12 times 21 is 252. Plus 48, so that becomes 300. Wow. Minus 1832, so 50 root 21. Cool. So then this becomes, we can represent this as 8 over 3, dividing through 6 minus root 21 over 6. Those cancel, and we end up with 4/9 of 6 minus root 21. And then remember that we have to do 1 minus that and multiply that by 15. So 15 times 1 minus 4/9 of 6 minus root 21 is our final answer. Let's write this out. Cool. So then that becomes, maybe take the 9 and divide over 3. 9 minus this plus this. Cool. That becomes 45, negative, so it's 20 root 21 minus 75 over 3. So the total here is 20, 21, 75, and 3. Right, so then the total answer is 41, 126, 120, what? 119, is that correct? A. That is quite, I mean, like, given that I got one of the answers, I'm pretty confident that it's correct. But yeah, this is something I probably should check. 21. And how are we doing on time? We have 30 minutes left. Okay, so we're actually kind of behind here. Set of numbers is called sum for you, where okay, I see. What's the greatest possible number of elements in a sum-free subset? Okay. Yeah, I guess like very basic bound is like, okay, clearly the number is at least 10 because we can have like all the odd numbers. Like if it's 1, 2, then it's 1. If it's like 1, 2, 3, 4, what's the best we can do? Can we have any 3? Well, 1, 2, 3 doesn't work. So then if 1, 1, 3, 4 doesn't work, 2, 3, 4 doesn't work. Yeah, so this gives us 2. I think the answer is just 10 here. By in whatever induction, whatever. We can probably come back to visit this problem again in the future. But I'm pretty happy with this. Okay. Radius are 1, 2, and 3. Cool. So basically you have a 3, 4, 5 triangle. I'm trying to like, I'm blanking. I think if they're all externally tangent, we can use. I just really forgot that there's a formula for this, but if we can do it the any other way. Let's see. Yeah, so in this case, what do we know about the angles? Not much. Guess we can draw this. Yeah, so I guess one thing we see is like I think it's either B or C from like memory, but yeah, one thing we can do is like figure out this height here, or like what is the area of this? Well, in this case, one thing you can do is like Heron's formula. So the semi-perimeter is 3 plus r. The area of this is given by that. And then similarly, semi-perimeter is 5 plus r, so we get yeah, I'm wondering if there really isn't a better way to do this. 5 plus r, 2 plus r, 3 plus r. This doesn't seem to be going anywhere. Okay, we do know this is a right angle, which should help. What is this? What is it? So this height is this, 2/3 of that. And then here it would be like 2/4 of root 4 plus r, 1 plus r, 3 plus r. And we know that the hypotenuse here is 1 plus r. Cool. So then I think we can just solve this. This is very fun. Pythagorean theorem, 1 plus r squared equals 4/9 of this, or 1 plus r, 3 plus r, 2 plus r, plus 1/4 of r, 1 plus r, 3 plus r, 4 plus r. Cancel. 1 plus r is 4/9 of r, 3 plus r. We can just like r 3 plus r. Multiply that with 4/9 of 2 plus r, so 8/9 plus 4/9 r, plus 1/4 of 4 plus r. That becomes r times 3 plus r times whatever this is, 17 over 9 plus 25 over 32r. And this looks gross, but then we can use our answer choices now, I think. Ideally, we want that 25 over 32 to go away. Is it 25? This is so ugly. I think I did something wrong. Oh. Area over, what is it? Sorry, this height is like area over base times 2. Yeah, so this looks correct. Yeah, this is really a time sink. I guess we can just do the rational roots theorem at this point and hope that the thing exists somehow. Yeah, so given that r is rational, this is like maybe less bad. The r cubed term is like 25 over 32. and it's like some factor of 32 over some factor of 25. This doesn't look good. I think probably just like something went wrong in terms of one of the calculations here. Oh my gosh. Okay. That is my bad. This should be 1, this should be 2. Okay, so that solves it. Yeah. Yep, okay, so then 1 plus r squared is actually sum of 4/9 of r 3 plus r times 2 plus 1/4 of r 4 plus r and then 1 and 3. So then that becomes 8/9 r squared plus 8/3. 8/9 r squared plus 8/3 plus 3/4 r squared plus 3r. 8/3 r there. Okay, sick. Cool. And then that equals r squared plus whatever. Cool. So then add up those. 32 plus 27. That seems weird. $36. I see a 23 showing up here. So this becomes 23 plus 11/3 r minus 1 is 0. Okay, so then 6 over 23 makes sense. 6 over 23 would give us 1 over 23 plus 11 times 2 over 23. Okay, so this works. 6 over 23 it is. B. 23. Okay. Cool. So then, what is this? 9, 15, 16. So what is the area here? The semi-perimeter is 20. Root 11. Multiply that by 5 squared now. Multiply that by 2 and then divide by 80. 25 root 21 over 2. Right. And what is this length here? 3/4 of 30. 25 over 2. Uh, right, so that's a ratio of what, like 5 to 6? So 5/11ths of this. (125√21) over 22. 125 multiplied by 1 squared plus √21 over 11 squared. Seems almost right. Maybe that √21's wrong. I think it's really like 23 or something. So that becomes like 12 or 11. Something's wrong. I'm sad. Wait, what? Wait, what is happening? BP? There's no. What did I? Oh, unlucky. It's this side, huh? Okay. That makes more sense. 35 over 2. That's 7/25ths of this? Yeah. This is like. Sorry, this is like a 7. Okay, yeah. And then this becomes what? Of this, which is 7. And then that becomes 7 times 5 or 2. 35 or 2, and then multiply this whole thing by 5 halves. Wait, what? I'm still wrong. 7. What is happening? What is happening? Well, I see a number 7, so I'm pretty sure the answer is D. I don't know what's happening. Cool. If fair if no digit is more than once, has no zeros, no digit is adjacent to 2 greater than G. Okay. So we can't have this. Gross. Rows. What? Okay. What are these problems? Probably makes sense to start checking work here. Trying to figure out when this happens. Because doesn't this mean the number looks like this, right? Some increasing segment followed by some decreasing segment. Yeah, okay. So if there's like n integers in this thing, then the apex is the apex. Then we pick each number to be either be on the left or the right. Arrange them in increasing then decreasing order. So then we just sum up 2 to the n minus 1 multiplied by some selection of, there's 9 different digits, so whatever this is, and we want that from 1 to 9. And that gives us some number. Yeah, so then this is just like 1/2 of like 2 plus 1 to the 9th power, and just like minus 1, I think. So 3 to the 9 minus 1 over 2. 6, 5, what is it? 6561. Multiply that by 3, it's like 190,000-ish, or 19,000. Divided by 2 is like 9,500. There's a C. It's close enough. Maybe it's actually, I feel like I should be checking work, but these problems are so fun. As a live solver, we gotta go for the contents. AP. Right, it's the longest when we... It's the longest when we're... Okay, so we have two conditions, right? Either AP is less than or equal to AB and then BP. So then AB less than AP occurs when we're inside this region here, this region. Sorry, AB is less than AP. Yeah. The AP is longer than AB, so it has to lie inside this, and then also AP is less than BP. Which is this here. So we need to be like here. Yeah, and then other cases BP, so I think it's this region here, where it's, yeah, okay, so then it's just the area of this region, which is pretty easy to calculate, I think. Yeah, so halfway, then this is a 60-degree angle. So this region, yeah, so then, what is this? 1/2, 1, root 3 over 2. The area of this is root 3 over 8, and then pi over 6 minus that, plus this area here. So I think to calculate that area, you would take so this is root 3 over 2, 1 minus that. Then the area of the entire region is root 3 over 8 plus yeah, so we want to do root 3 over 8 plus 1/2 times 1 1/2 of that, and then minus pi over 12. Yeah, so this combines to pi over 4. Then we end up with pi over 4 minus root 3 over 8 plus root 3 over 8 plus 1/2 of this. So the answer is just I plus 1/4, sorry, 1/2 minus root 3 over 4. Cool. So then, what is this? This feels too small. What happened? Oh, sorry, this becomes pi over 12. So this becomes 12, this becomes 6, this becomes 3. So 6, 1, 3, 3, 12. Those add up to some 1 mod is 25. Cool. How much time we have? 6 minutes. I think we have something for every question now. So let's just look at the ones we starred real quick. Number 19. We're adding 3, then 2. Yeah. And then how many times do we add? Well, there's 13 rows. We want to get to the 13th row. We add 12 times, and we add numbers from 3 to -8. So that gives us -8, -7, -6, -5, -4. Wait. That's -23. Wait, what? What is happening? 6, 5. Nope. I'm just bad. Okay, yeah, it's -29. Okay. That looks correct. Is there any potential for off by ones? I feel like it's hard to believe that I'm off by 1 here, right? Like these are all like very big numbers. 75 plus 2095 plus 24, 119. Pretty confident in that one. Okay, number 21. Sum free. Okay, the sum free thing. How would I justify it? Well, clearly we can't add anything else to this because this generates every even number. Why can't we do better than this? There's probably some pigeonhole argument. It's probably not worth thinking about that too much. Let's look at I'm pretty sure I'm correct here. Okay, let's look at 23 for sure. We have 4 minutes to figure out what went wrong. Yeah, so 45, 75, 80. Sorry, this should be B, this should be A, and this should be C. This altitude is a weird number. This bisector here, this is calculated to be 35 over 2, and this is 125 over 2. This is some number. We need to find this length here. Then let's multiply through by 2/5. So this becomes 18 and 7. Then this is square root of 324 minus 49 is 275. Root 275 is like 25 times 21, right? So then, or no, it's not. 25 times 11. Okay, so root 11. 5 root 11. This is 7/25 of that. Ah, I see. So then this is like this, right? 7 times 4/5. So this is 7 times 5/5. So 7 times 6/5. Multiply that by 5/2. You indeed get 21. Happy. Okay. Nice. I did put 21, right? D. Yeah, okay. What else can I check? I have 2 minutes. Probably something earlier. Let's check number 18. Okay, so the sum of the roots is 4. The product is -3. The ratio, the sum of the things is -4 thirds. So 1/2 of that is -2 thirds becomes -3 halves. And all of the roots are real, right? Yep, all the roots are real. Sick. So that's good. I'm happy with these ones. 1 minute. Got this round table question. Yeah, I mean, I got it 2 different ways. Good, good, good. Sound like that makes. Um, how happy are we with this one? Oh, what am I doing? What am I doing? Shoot. Okay. 36 times 12 is whatever this is, 432. Plus 32, 464. Oops. That was almost as silly. Neither prime nor even. Those are only 1 and 9, right? Okay, let's hope that was the only silly I made, I guess. Yeah. So that, okay, time is up, time is up. There. I hope the answer wasn't actually D. I think we're chill. I think we're chill. Let's see. Uh, Answer key? I made some dumb error somewhere else. Sick. E, B, A, E, C, E, B, D, C, E, D. Nice. D. Okay. 14, B, A, D, E, B, A, A, C, B, D, C, A. Perfect score, guys. Let's go. Yeah, so that was the only silly, luckily. All right, nice, 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 nice. That feels good. That feels good. All right. Yeah. So for, um, I guess that's the first. I think that's the first perfect score I got on from a Livesolve. Yeah. So I guess now you open the stream to any questions. If there was anything you wanted to see in more detail, or if you were like curious about my thought process about any of these, I think some of these problems were definitely very challenging. I noticed that for this test, as a like a like a general thought, is just like a lot of these questions are very like stock. Like for example, this problem 22, like I think I forgot. Is it? um, some dude whose name was start with D. Descartes circle theorem. So it turns out that for the four mutually tangent circles, you have this like nice theorem about uh, it's like the sum of the radii, and since these are all externally tangent, they're all positive signs, is like I think it's like double the sum of the squares. Yeah. So this would have been like this would have solved the problem immediately. You just get like 6 plus r4 equals 2 times 1, 2, 3, all squared is 14. And so you just solve this, and now you get like 6 over 23. Yeah. So I think it's called the kissing theorem. Interesting. I see as just Descartes' circle theorem, but I also see, yeah, kissing theorem here. Yeah, if you're using this theorem, just be careful. Like, there's also cases where like there's like a big circle that contains 3 smaller circles, and in that case, I think you have to make the outer radius negative in like here. I think otherwise this theorem just works. I think there are also different cases where I think this extends to like other situations, but this is like a very well-known result that you should be comfortable with. Cool. Can you explain the fair number thing from problem 24? Yeah, sure. Yeah, so I think this one was like actually a pretty impressive solve for like 2 minutes. But basically the idea is, um, first of all, like really what I'm thinking about is doing casework on the number of digits. We know that there's at most 9 digits, so there are 9 different cases. Let's take a look at one of these cases, where you have 6 different numbers chosen from the set 1 through 9. As just an example, right? We see that like what does the thing first of all restrict? It restricts on the order of the numbers. So let's just because of that, let's just say like without loss of generality that the numbers are like 1, 2, 3, 4, 5, 6, because the actual identities of the numbers don't actually matter that much, just the order. So so for example, there's like so that gives us like 9, choose 6 ways to pick the 6 numbers. And then what else do we have? Well, we now need to find the number of ways to order these numbers, right? Normally, we're not restricted, so we just have 6 factorial. But actually, in this case, we are restricted in that we can't have any number that is lesser than both of its neighbors. So I just want to, the way I drew this is like, visualize this is like there's no valleys, right? And what is something with no valleys? Well, it has to be a mountain. And what I mean by that is that, like, basically we can't go, if we look at, like, if we label we go from left to right and label every step as either decreasing or increasing, I guess we can draw, like, up an arrow and a down arrow, then we can never have a situation where we have an up arrow followed directly by a down arrow. If we have 6 numbers, we'll have 5 of these either ups or downs from left to right, right? So if you have 6, then like there's 1 up or down here, 1, and over here. And we can see that when we have this situation, like we have like up, right? And remember, we cannot have this pattern of up, down, right? Or up, down. So what this actually restricts us to being is only having downs followed by, sorry, we cannot have a down followed by an up, right? This would be a down and this would be up. We can't go down and then go up. So then the only thing we can do is go up some number of times and then start going down, right? And in no point can we ever have a down followed by an up. So in fact, we can only have basically 1 hump here. If we have 2 humps, we have created a valley. That is bad, right? So we now have seen that we basically have the numbers 1 through 6. They must form some sort of mountain formation. And now, the really interesting thing now is like, Okay, now we need to pick numbers to be on the left of this hump and on the right. And we also know the key observation is that this top of the mountain is the largest number. So we have 6, and then we need to figure out a way to like distribute the numbers 1 through 5 on the left and the right of this mountain. So one possible way is to have, like, for example, for the partition 1, 3, 4, 2, 5, this yields the number 1, 3, 4, 6, 2, 5, or 5, 2, because we have to go increasing then decreasing. And notice how every partition of the numbers from 1 through 5 gives us a unique solution here, right? 1, 3, 4, 6, 5, 2 is in direct correspondence with this subset that we chose to be on the left. So actually, the total number of mountains we can construct, where 6 is on the top and some subsets on the left and some subsets on the right, is exactly equal to the number of non-empty or even empty subsets of 1, 2, 3, 4, 5. Right? Yeah, so once we get to that point, sick. Okay, that just means that there's 32, right? And we can verify, right? If we pick an empty set, right? If we choose none of the numbers to be on the left, then they're all on the right. That results in the number 6, 5, 4, 3, 2, 1, which is valid. And similarly, if we choose the entire set to be on the left, we end up with 1, 2, 3, 4, 5, 6. So these are both good. So then we end up just with 32 different ways, having fixed the 6 numbers we want, and remember that they're all distinct, to have to like arrange those digits. So for this case, the total number is 926, different ways to select the numbers, times 2 to the 6 minus 1, right? Because we know that 6 is in the middle here at the top. So then that gives us, for case 6, where we have picked 6 numbers, there's this many. So this many 6-digit solutions that are fair. Then we can just see that it's just like, we just add those, right? So we there has to be at least one digit. So we end up with this summation here, which I came up rather quickly. And then to solve this, this looks pretty similar to the binomial expansion of, in particular, 2 plus 1 to the 9, right? And that would be like summation of 2 to the n times 9 choose n from 0 to 9. We see that we're indexing from 1 because there has to be at least one digit. So this differs in 2 big ways. One, there's a 1 less factor of 2 in each of these terms. And 2, that the n equals 0 index is missing. So we have to start with 3 to the 9, subtract out the n equals 0 term, which happens to be 1, and then divide the whole thing by 2 to get from 2 to the n to 2 to the n minus 1. And so this is our final answer. And that turns out to be the number 9841. And we can just like, during the test, right, I was kind of like panicking because this was I only had like 6 minutes at this point. I was like, oh, okay, what do I do? I ended up just like saying, okay, I know 3 to the 8 is 6561. Multiplying by 3 again gives us like about 19,000. Divide that by 2 to get like 9,500 approximately. And the answer choices obviously help here. But yeah, like because they're so spaced far apart, you actually did notice that for problems 22, 23, and 24 that I used the answer choices to guide me to my solution, right? So for example, like 22, I was like, let's use the rational roots theorem. 23, I was like, or like seeing that the answer was rational, I was like, okay, it's the rational roots theorem. 23, I saw the answer had to be an integer, and I had a factor of 7 that I didn't think was going to go away, so I just picked the only multiple of 7. And then 24 is just like an approximation thing. But yeah, so let's just like verify that this gives us the correct number. 19683 minus 1 divided by 2. That gives 9841. Yeah, so that gives the correct answer. So yeah, that's problem number 24. I see. So there's some I guess any other requests for solutions, and then uh oh the six was just an example, right? I just like said like like for the case where there's n digits, the term is here, and then we just like sum that up from n equals 1 to 9. Um, cool. In terms of cutoff predictions, I haven't really been in the sort of AMC sphere in a bit. Given that I got a perfect score, like maybe it's a bit higher, but also considering like yeah, so I think a lot of the later problems specifically were a lot more approachable than in previous years. A lot of them can be like mems, like memorized. So for example, 22 is memorizable. I think 21 is also like a pretty common thing to see. um, and a lot of these like some of these other questions, like I feel like the mid part of the test was just like pretty hard comparatively. Like maybe like 1 through 16 were fine, like pretty normal. I think number 12 was especially tricky. Number 18 is like just a weird problem, but I don't think it's like super hard. I think like especially like there's just like certain problems that I think were like really weird. I would say like if we looked at sort of the difference of this 10A from previous 10As, I would say the like 1 through 15 are maybe like decently easy compared to the rest. 16 through like 20 are especially hard. Then 21 through 25 are like on average about as easy. Maybe 24 is an exception. But yeah, you saw me struggle with problem 22 because I didn't know the kissing theorem, right? Like I ended up, making it work, right? Because of this like nice right angle they gave me. Actually, without this right angle, I think this problem would have been like much harder, or like it probably wouldn't have been as nice. So I'm grateful for that. Yeah, so I guess like if I were to put a number, I don't know what it's been in past years. I think probably higher than last year's is very reasonable by maybe three to 6 points. Yeah, that would be my inputs. Um, yeah, so let's see, what was the cutoff last year? Uh, from 2024. Interesting. 94.5. I see. So probably, I think 96, from 96 to 99 is like reasonable. I did see some inputs that said you thought it was easier. Interesting. Um, Apparently 1 through 15 was the hardest it's ever been. I'm like, you have to take everything I say with a grain of salt because I haven't been competing like specifically in the AMC for a very long time. Just personally, like I scored better on this 10A than in the previous year, I think, unless I got another perfect. I seem to remember I didn't do so well um, on that last year's test. I think it's also on this channel. We can take a look. Uh, yeah, so let's see. Let's see. We're probably gonna wrap up very soon, but let's check. Last year, I got this Livesolve here. Where's my Livesolve? Okay, my playlist here from 2025, 2024.
Build a website.
139.5 from last year. That's a pretty significant increase, right? Going for 139.52. Perfect. But I think like also considering the type of student, um, I think yeah, like there was a lot of like bashing that you had to do. It was very easy, I think, for this test specifically to get stuck on a problem for a long time. Just make sure that you're, yeah, so you probably like, make sure that when you're taking the tests in the future, like on the 10B, for example, that you're especially careful about not getting stuck on a specific problem. For example, number 22 is a one-step theorem type problem. And if you've just forgotten the theorem, maybe it's better for you to just move on. I guess in my case, I was like, I can probably just like muscle it out with a bit of bashing when you saw I made many mistakes. And so that could have gone very wrong for me. You also saw that I didn't have very much time to check. And like actually by miracle, I found the only silly that I made the entire test, which was kind of crazy. Yeah, so things could have gone definitely worse. I think like I deserved probably like a 144-ish, which means that's an improvement of like 6 points approximately. And so if that were to translate into sort of like a cutoff, I think that would translate to about 3 points. Probably not the full 6 points, because we're talking about like a cutoff. So I think it should scale like proportionally. So from like 138 to 144, just apply that ratio to like 90. What was it? 94.5 from last year. I think it's like probably around 97.5. I think that would be my most confident guess. But given the input from some of the other competitors in the chat, it's entirely possible that it's actually lower. So yeah. What was my thought process for 12? What was number 12? Oh, fun. The password. Yes, so let's go to my work. For number 12, it's a basic combinatorics problem, but like it's very easy to get lost in sort of the casework. Again, this is a casework. And it's actually like in the problem statement, it kind of suggests that you should use casework. For example, here, exactly one digit is even, exactly one possibly different digits prime. So you really want to think about when can those digits actually be the same digit and when can those digits be different. So we do two cases. So then once we do those two cases, now it just becomes like a decently easy like combinatorial problem where we have, okay, imagine the same digit is both even and prime. Well, there's only one even prime, so that has to be 2. And then we cannot have any more even numbers. We can't have 0 as given. And we also can't have 3, 5, or 7 because those are prime. So the only numbers remaining are these ones on the end, 1 and 9. So we can see here that we have like locked in the number 2. And then we have like the other numbers have to be like 1 or 9. So given a 4-digit number, there's 4 ways to place that 2. And then 2 ways to select what the other numbers are, right? So these are all 1 or 9. So there's 2 selections for 4 times 2 cubed. That gives 32. That's the small case. That's like the easy case. How about this other case here, where we have a prime and an even number, which are different numbers, right? So in that case, specifically, to make sure that we don't double count stuff and we make sure we're not doing weird things, like the prime number has to not be 2 and the even number also has to not be 2. And that is actually like very trippy, right? I actually included 2 in the even numbers because that slipped my mind. So then I think when I went back to review the problem, I was like, oh, why is the number 2 here? Like that's a prime number. And then that led me to correct my answer. But yeah, like the number has to, the prime number can't be even and the even number can't be prime. That gives 3, 5, or 7 for the prime, 4, 6, 8 for the even number, and then the remaining 2 numbers can be neither even nor prime, so they're 1 or 9. Same in the previous case. Then the way I calculated this was, okay, let's first make sure that we account for the number of ways to rearrange these groups. So you can think of these each as like one letter, like for example, A, B, C. We see that there's 4 factorial over 2 factorial or 12, different ways to rearrange those groups. And then we have to make the individual selections. So 3 choices here, 3, 5, or 7, 3 choices here, 4, 6, or 8, and then 2 choices for the 1 or 9. So that gives us an answer of 12 times 3 times 3 times 2 times 2. That would have given us 432. And then we just add the 2 cases together, 432 and 32, to get an answer of 464, sorry. And that gives us D. I also got a 145 point. That's pretty good. It's pretty good. Wow. I see some more questions in the chat. Let's see. Is AlphaStar good for like getting good at AMC? I would say so. I was once an AlphaStar student. Their level like 30 classes I think are very, very good for sort of getting like those stock questions correct. And you saw that paid off in this specific test because of the number of stock questions, like 22. So being just familiar with sort of the landscape of the AMC, what types of theorems you need to know, that's where AlphaStar comes in. It's a huge resource, I think, for me personally. And I really enjoyed doing their summer camps. I think they also have winter camps that you can do. But yeah, like as a previous student, I think that helps me a lot. Yeah, and then AlphaStar, is it mainly lecture and homework or like self-study? So there's 2 different tracks. Like AlphaStar, I think primarily originally did a lot of like lecture homework style like things, but also like we now have like an online portal with like a bunch of problems that you and like we have created like sort of booster classes that are more focused on like sort of those assignments rather than like lecture format stuff. So I think like if you just look at the website, I think there's a lot of the AlphaStar website. There's a lot of resources, different styles of learning. I think it's very inclusive in that way. So if you're more of a self-study person, you might want to take like a booster class in conjunction with like sort of like, so that gives you like the materials to succeed, but of course you need to put a lot more work into it as like a self-studier. But if that's more effective for you, I would highly recommend. How does AlphaStar? Yeah, so like it's just mostly like summer, winter camps. Mostly, they do things in math competitions, but also in coding and physics. So you can take a look at that. AOPS is also a great resource, right? It's free, it's open source. I think I definitely grew up with AOPS. Is such a great help. I think I've done like basically every AMC in the past, so I've definitely used it a ton. And it's also just like I don't know what the forum is like nowadays, but I think there were a lot of fun things going on in the apps. I've also bought some of their books, so like I think intermediate algebra and some combinatorics and geometry stuff that I think some of AlphaStar's courses are like pretty inspired from those. I would say like they're decently similar. So if you want to invest in a book or two, like that's also a decent resource. What would you recommend preparation-wise to qualify for AMY or DHR, apart from past papers? Yeah, I mean, yeah, good question. For preparing for AMC, yeah, like the number one thing I will say is like just doing past tests, because that gets you familiar with what you need to work on. You also really want to like I think just doing other competitions in general, like I think there's a very, very much like a shared aspect of many different competitions, like high school competitions. If you're from the US, like all of these like college competitions like BMT, SMT, HMMT, those are really fun, and I think they also like help you like build your knowledge base for this type of problem, this type of like test. So I think that's also super useful. For me, reading books was like less of an emphasis, like, but definitely like, I think you kind of just got to get a feel for it, right? Like there's some level of intuition that you need, and that stems from being very comfortable with the sort of content that the AMCs provide. But in order to do that, you need to I think the best way is to absorb from past tests. Yeah, so just do more competitions in general. I think see if you can see if your school sponsors or is running any sort of tournaments, or see if they're getting sending a team or something like that. AlphaStar also fields teams for many of the top contests, so if you want to try and get experience through there, I very much welcome you to try. It is very competitive. I think it's very, very rewarding. To get to JMO HM. Yeah, so for JMO, I think to do well on a proof-based competition, first of all, I think the biggest thing and the easiest thing you can do right now is just get better at writing a proof. That involves being persuasive, convincing in your words, and also being very concise. So making sure you're writing in a way that is not intentionally confusing as well as easy to follow. So I would recommend being able to read your own solutions and not wincite your own writing at least. There's a lot of AOPS. If you just look at JMO's solutions, one thing I would really recommend you to focus on is sort of the structure of a proof, making assuring the reader, a good proof assures the reader that they will get to their destination and kind of tells them what sort of stops are along the way. So we will show that this is true. So that's a big thing. In terms of actually doing proofs, I think the same type of problem solving applies. The same type of problem solving technique applies. So if you've been prepping for AMC, I think Usagmo is a much smaller sort of leap than you might think. But I do think that there's definitely a couple topics that are maybe exclusive to JMO. I think it just involves a bit more rigorous number theory. For example, really thinking about sort of for example, I think what I will say is every problem that was written for an AMY can be probably can be turned into a USMO problem with some alterations. So I think you're pretty likely to do better on the USMO by just doing preparing for AMY type questions. And then my advice for all this stuff is just do past problems. There really isn't anything that beats it. And then of course if you need I think one thing that AlphaStar's courses does particularly well is basically takes important things, important motifs, important question types from different disciplines like geometry, you have power of a point or different techniques in synthetic geometry that is very popular among USMO problems, and sort of breaks them into chapters, and it becomes very easy, at least for me, to digest. So I think also AlphaStar or a similar course would help you with that. Just oh, these are the things I need to focus on. These are the topics, and here we've done it in such a way that kind of gives you a lot of practice intrinsically by binning these problems into different categories. Then you can just pretty easily figure out pretty easily have access to a lot of problems that fall under this problem solving technique or this topic in geometry or number theory or whatever. So yeah, definitely that's I think one thing that you could definitely invest in. Yeah, so that is my 2 cents on how to prepare for math competitions. I know you all have a 10 or 12B in the future, in your very near future, so I would recommend you to get some rest, really emphasize that, get some good sleep, and just all the standard test taking stuff, right? Just make sure you feel very comfortable with the room, make sure you have enough scratch paper, and just enjoy the test. And that's kind of the ultimate goal, right? You just want to be there to enjoy the problems, the problem solving, And I think like if you're not enjoying the moment, then you're probably doing something wrong. So I really, really recommend you to focus on that. Yeah, and best of luck to your 10, 12Bs. And we'll have another stream popping up shortly for the AMC 12A. So if you want to check that out, that should be on the same channel. Yeah, I think I said like 90. I think I said like 97.5 was like probably the most likely prediction. But yeah, thanks everyone for joining. I really enjoyed talking to you guys and happy that I got a perfect score. I will see you soon.